Here is something about aliens that nobody ever stops to think about. Not whether they exist, not whether they're watching us, not whether those blurry videos from Navy pilots are real. Something far more specific than any of that, and honestly, something far more unsettling once you actually sit with it, even if aliens exist. Even if right now, as you're listening to this, there are a million thriving civilizations scattered across our galaxy, some of them so advanced they make our entire history look like a rough draft. They are never coming here, and we are never going to them. Not because they don't want to, not because of some cosmic misunderstanding, but because of something so fundamental, so baked into the architecture of reality itself, that no amount of technological progress is going to bulldoze it away. Welcome to Feynman's path. Today, we're going to take this idea apart piece by piece, not to make you feel small, and not to kill your sense of wonder, but to do something I think is actually more powerful, to show you what the universe really looks like when you stop wishful thinking and start actually calculating. Let's start with a story. It's 1950. The place is Los Alamos National Laboratory in New Mexico, the same facility where, just 5 years earlier, some of the most brilliant minds on Earth had assembled to build the first atomic bomb. The war is over now. The physicists are back to doing what physicists do, which is argue about everything. Richard Feynman is there, Edward Teller is there, a few others. And on this particular afternoon, they're walking to the cafeteria for lunch, and the conversation drifts, as it often did among that crowd, into speculation about flying saucers. This was peak UFO mania in America. Every tabloid had a new story. Every small town had a witness. People were losing their minds over little green men. And these physicists, being physicists, are doing what physicists do, running the numbers in their heads while they walk. They're thinking about the galaxy. Our galaxy, the Milky Way, is roughly 10 billion years old. It is, by any reasonable measure, enormous, 100,000 light years from one end to the other. And packed inside it, somewhere between 200 and 400 billion stars. Now here's the question. Feynman started turning over in his mind. If even a tiny fraction of those stars have planets, and even a tiny fraction of those planets develop life, and even a tiny fraction of that life develops intelligence, and even a tiny fraction of that intelligence develops technology, you're still talking about potentially millions of civilizations, maybe more. And the galaxy has had 10 billion years to cook all of this up. So they sit down at lunch. Feynman picks up a napkin. He starts scratching out some rough calculations. Nothing fancy, just back-of-the-envelope stuff. If some civilization out there built a spacecraft, not a sci-fi miracle machine, just a modest nuclear-powered rocket, they could hop from star to star. Take their time. Stop and rest at each system, even moving at a leisurely pace, hopping from one stellar neighborhood to the next. The math says they could colonize the entire galaxy in somewhere between 10 million and 100 million years. Which sounds like forever to us. But against the backdrop of 10 billion years, that's nothing. That's less than 1% of the galaxy's age. Which means if any civilization anywhere in the Milky Way got its act together, even a billion years ago, they should be everywhere by now. They should have been sitting at this table with us. And then Feynman looked up from his napkin and said something that people would be quoting for the next 70 years. But where is everybody? That question became known as the Fermi Paradox. Not because Fermi invented the question, Feynman was there too, after all, but because it captured something that was bothering every thoughtful person who looked at the math. The numbers say the galaxy should be crawling with civilizations. Our own existence proves that life and intelligence can emerge. So why the silence? Why the emptiness? Why, after decades of scanning the sky, have we never once picked up a single unambiguous signal from anyone else? Now, there are a lot of proposed answers to this question. Some of them are genuinely terrifying, some of them are poetic, some of them are just wishful thinking dressed up in fancy language. But here on Feynman's path, we go after the most physically honest answer. And I think when you actually do the physics, when you sit down and calculate what it would really take to cross interstellar space, the answer becomes surprisingly clear. The problem isn't that civilizations destroy themselves. The problem isn't that we're in a cosmic quarantine zone. The problem isn't even that aliens are hiding from us. The problem is space itself. The raw, stupid, merciless, staggering emptiness of it. Let me show you what I mean. The closest star to our sun, not our sun, the very next one in line, is Proxima Centauri. It sits about 4.2 light years away, which means light, traveling at the fastest speed anything in the universe is permitted to travel. 300,000 kilometers every single second takes 4 years and a couple of months to make that trip. Now, how fast can we actually go? The fastest human-made object in history right now is the Parker Solar Probe, a spacecraft we launched in 2018 to study the Sun up close. At its top speed, swinging around close to the Sun, it hits about 700,000 kilometers per hour. That sounds incredible. And in everyday human terms it is. It would get you to Proxima Centauri in about 6,900 years. Let's call it 7,000 years. 7,000 years ago, human civilization was just barely learning to write. Sumer was just starting to scratch pictograms into clay tablets. The Egyptian pyramids hadn't been built yet. The entire recorded history of our species hadn't happened yet. And at our fastest speed, that's how long it would take to reach the single nearest star. Now I can already hear the objection forming. That's our technology. That's primitive by any advanced civilization standards. What if aliens have something much faster? Fair enough. Let's give them something much faster. Let's say some civilization out there has mastered propulsion we can barely imagine, and their ships can travel at 10% the speed of light. That's 30,000 kilometers per second. It's 300 times faster than our Parker Solar Probe. No human engineering has come anywhere close to this. How long to Proxima Centauri at that speed? 42 years. 42 years to reach the single nearest star. Most stars aren't the nearest star. The average distance between stars in our part of the galaxy is closer to 5 light years. If you want to reach a star 1,000 light years away, traveling at 10% the speed of light, you're looking at 10,000 years. 10,000 years. Now here's where it gets worse. Because even if we hand-wave away the travel time, even if we say fine, a sufficiently advanced civilization could somehow compress the journey or put their crew into suspended animation or send robots instead of people, there are still problems that don't go away. Problems that are not engineering challenges. Problems that are baked into physics at a much deeper level. Problem number 1. Space is not actually empty. This sounds strange because when you look at pictures of deep space, it looks like the most vacant thing imaginable, and compared to anything on Earth, it is. But in the interstellar medium, the space between stars, there's still roughly 1 atom per cubic centimeter floating around. Sometimes a little more. A few hydrogen atoms here, a helium atom there, the occasional bit of cosmic dust. At everyday speeds, this is nothing. You'd never notice it. At relativistic speeds, at a meaningful fraction of the speed of light, those same atoms become bullets. If your ship is moving at 10% the speed of light and it collides with a grain of sand, not a boulder, not a pebble, a single grain of sand, the kind that gets stuck in your shoe at the beach, the impact energy is rough Kali equivalent to a nuclear weapon. A real one, a city killer. And space isn't just populated by grains of sand. There are micrometeorites, dust particles, tiny shards of ice, little fragments of rock. At high enough velocities, any one of these could be catastrophic. So, you need shielding. To protect a ship from high-velocity particle impacts at 10% the speed of light, you'd need to surround it with something like a meter of water or an equivalent thickness of some other dense material all around the front of the vehicle. Maybe more, depending on the route, which means your ship just got dramatically heavier. Which brings us to problem number 2, energy. To accelerate mass, you need energy. The faster you want to go, the more energy you need. And the relationship isn't linear as you approach a significant fraction of the speed of light. The energy required climbs in ways that are physically brutal. Here's a number to chew on. To accelerate just 1 kilogram, about 2 pounds to 10% the speed of light, you need roughly 450 terajoules of energy. How much is that? That's approximately equal to the total amount of energy consumed by the entire United States in about 5 seconds. To accelerate 1 kilogram. Now take your spacecraft. Add the shielding. Add the fuel. Add life support. Add crew quarters. Add supplies for a multi-decade journey. Add whatever scientific equipment you're bringing. A real interstellar spacecraft would be massive, hundreds of tons at minimum, probably much more. Multiply that mass by the energy cost per kilogram. You are now talking about energy on a scale that beggars description. The total energy output of our Sun over several years, pointed entirely at one spacecraft, might do the trick. And that's just to get there. You'd need roughly the same amount to slow down once you arrive. Otherwise, you just fly through the target system at 10% the speed of light and keep going into the void forever. Someone's going to say, what about antimatter? What about fusion? What about physics we haven't discovered yet? These are reasonable questions. Let's take them seriously. Antimatter. Yes, it exists. Yes, Matter-antimatter annihilation is the most energy-dense reaction we know of 100% mass to energy conversion. Beautiful in principle. But to produce antimatter in quantities useful for propulsion, you need particle accelerators, enormous amounts of energy to manufacture it, and incredibly sophisticated containment systems to keep it from annihilating prematurely. To get enough antimatter to fuel an interstellar ship, you'd need to convert something like an entire planet's mass into energy first. It's a bootstrapping problem that doesn't resolve itself. Fusion, also appealing. Clean, efficient, powerful. We've been trying to build a practical fusion reactor for 70 years. As of today, we still haven't produced a sustained reaction that outputs more energy than we put in. Even if we crack it, and I think we will, a fusion rocket produces nowhere near the energy density needed for relativistic travel. The math puts it well below what's required. What about physics we haven't discovered yet? This is where I want to be careful, because people often invoke unknown physics as a trump card, a way to make any objection disappear. But there's something important to understand about how physics actually works. Over the past few centuries, our understanding of the universe has undergone several complete revolutions. Newton gave way to Einstein. Classical physics gave way to quantum mechanics. Each time we thought we had the final picture, the universe turned out to be stranger and deeper than we imagined. But here's the thing. Every time we've expanded our understanding, the new physics hasn't made previously impossible things suddenly possible through some convenient loophole. What it's actually done is confirm, with much more precision, why certain things are impossible while revealing entirely new and different impossibilities we hadn't thought of before. Light speed as a limit is the classic example. Before Einstein, people simply assumed that if you pushed something hard enough for long enough, you could eventually outrun a light beam. There was no known reason you couldn't. Then Einstein came along and explained exactly why you can't, not because of some arbitrary speed limit that future engineers might bypass, but because the structure of space-time itself is built such that the speed of light is a fundamental constant woven into the fabric of reality. Mass, energy, space, and time are all interlinked in a way that makes exceeding light speed not merely difficult but categorically impossible. The more energy you pour into accelerating a massive object, the more mass it effectively acquires, and the more energy you need to accelerate it further, an infinite regress that converges at light speed as an unreachable ceiling. This isn't a gap in our knowledge waiting to be filled. This is one of the most thoroughly tested and verified principles in all of science. Now, someone is definitely thinking about warp drives and wormholes, because these are the traditional escape hatches from this argument, and I want to give them the respect they deserve. Warp drives, specifically the Alcubierre drive, proposed by physicist Miguel Alcubierre in 1994, are a genuinely fascinating idea. The concept is elegant. Instead of pushing your ship through space, you compress space in front of it and expand space behind it. The ship sits in a little bubble, effectively surfing a wave of space-time distortion. And Alcubierre showed mathematically that Einstein's equations don't explicitly forbid this. But here's what the math also shows. To create that warp bubble, you need what physicists call exotic matter, a substance with negative energy density, meaning a material that is less than nothing, more negative than vacuum. We have never observed anything like this. We have some theoretical hints that quantum effects might produce something in the right ballpark under extremely specific conditions, the Casimir effect, for instance, but the amounts are infinitesimal, and scaling them up to anything useful is nowhere on the horizon. Some more recent analyses suggest the energy requirements might be merely equivalent to a few solar masses of exotic matter rather than the entire observable universe, which is not exactly reassuring. Wormholes face the same exotic matter problem. To hold a wormhole open long enough to pass through, you'd need exotic matter propping up the throat. And even if you somehow produced this exotic matter and constructed a traversable wormhole, you'd still need to physically transport one end of it to your destination first, which means someone had to make the trip the hard way before the wormhole becomes useful. I want to be precise here. Warp drives and wormholes are not magic tricks. They're serious theoretical physics. But the key word is theoretical. They require ingredients that may simply not exist in the universe. Saying we'll use a warp drive to solve the problem of interstellar travel is like saying we'll use a perpetual motion machine to solve the energy problem. The math might look superficially plausible, but you're betting on the universe containing something it has given us no evidence of containing. Now, here's something that doesn't get talked about enough. Even if you could solve every physical challenge, the energy, the shielding, the speed, all of it, you'd still face the most quietly devastating obstacle of all: time. Let's say you've built an incredible ship, 10% of the speed of light, properly shielded, powered somehow. You're heading for a star system 1,000 light years away. For the crew on board, due to relativistic time dilation, the journey might feel like a few decades. Manageable, maybe, if they were born to the mission. But for the civilization that launched them, 10,000 years pass. 10,000 years. In 10,000 years, the civilization that launched that ship will be unrecognizable. Languages will have transformed beyond comprehension. Governments, nations, religions, economies, all of it reshuffled many times over. The organization that funded the mission will be a footnote in history, if it's remembered at all. The people who cheered at the launch will be dust. Their children's 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 children will be dust. The very concept of us that motivated the mission will have been replaced by something else entirely. Who, precisely, is supposed to maintain funding and political will for a project whose results won't come back for 10,000 years? This isn't a solvable problem. It's not a matter of institutional design or long-term thinking. No human institution has ever survived 10,000 years intact. The oldest continuously operating institution on Earth, arguably, is the Catholic Church, roughly 2,000 years old, and it has changed so dramatically over that time that its founders would barely recognize it. 10,000 years is 5 times that. And we're talking about a mission to one star system. One. But wait, here's the thing that really gets under my skin when I think about this carefully. Let's say some civilization does launch such a mission. Let's say they somehow maintain cohesion and purpose across the millennia. Let's say the ship arrives. What do they find? The honest answer is almost certainly nothing interesting. The universe is enormous, and habitable worlds with life on them are not common. Worlds with complex life are rarer still. Worlds with intelligent life at a comparable technological level to your own, at the exact moment you happen to arrive, are so improbable as to be essentially vanishing. Think about what that means. You've spent unimaginable resources. You've crossed 1,000 light years. You've waited 10,000 years. And you get there and find microbes, or nothing, or an ocean world with creatures equivalent to Earth's fish, or a dead rock. What was the point? This is what I think people miss when they imagine interstellar civilizations expanding across the galaxy. They imagine the expansion as something like European colonization ships going out, finding rich new territories, bringing back resources and knowledge, establishing settlements that feed back wealth and information to the home civilization. But that's not how interstellar travel works. The distances are so vast that there is no feedback loop. By the time your expedition returns, if it returns, the civilization that sent them is gone. There is no empire. There is no network. There is only an isolated, expensive, one-way journey into the dark. Here's a useful analogy. We have the technology to send submarines to the deepest parts of the ocean. We do it occasionally, but we don't build cities on the ocean floor. We don't have permanent colonies 10 kilometers underwater. Why not? Because it's extraordinarily difficult, extraordinarily expensive, and the benefit doesn't justify the cost, even though the deep ocean is right here on Earth 5 miles down. Now imagine that the deep ocean were 4 light years away instead of 5 miles, and 10,000 light years away in every other direction. That's the situation. Let me take this one step further, because I think the communication angle is worth examining. If physical travel is impossible in any practical sense, what about radio signals? What about sending information rather than people? This is genuinely more feasible. A radio signal travels at the speed of light. No energy cost beyond the broadcast itself. No crew to keep alive, no shielding to maintain. Just a pattern of electromagnetic waves propagating outward through space. So why haven't we heard anything? Well, for one thing, our galaxy is 100,000 light years across. A signal sent from one side takes 100,000 years to reach the other side. If some civilization sent a greeting from across the galaxy before the last ice age ended, we might receive it next Tuesday and have absolutely no way to reply until the year 102,026. Even for neighboring civilizations, the conversation timescales are absurd. Signal to a civilization 500 light years away, 500 years for your message to arrive, 500 years for their reply. 1,000-year conversation for a single exchange. And that's assuming they're broadcasting at all. Why would they be? Sending a powerful signal into the galaxy requires significant energy. It also announces your existence to whoever might be listening, and you have no idea who that might be. If there's any chance that some of the other civilizations out there are predatory, hostile, or simply indifferent in dangerous ways, broadcasting your location is a remarkable thing to do voluntarily. This idea that advanced civilizations might deliberately stay silent out of self-preservation has been called the dark forest hypothesis, after a novel by the Chinese author Liu Cixin. The image is stark. Imagine a dark forest filled with hunters who don't know where the other hunters are. The rational strategy is to move quietly, never reveal yourself, and shoot anything that makes noise before it can become a threat. In such an environment, the civilizations that survive are the ones that never advertise their existence. Now, I'm not saying I believe this is the primary explanation, but it's worth noting that if even a small fraction of civilizations behave this way, the observable universe would look very much like what we actually observe. Silence. I think the most probable explanation is simpler and more mundane than predatory aliens or cosmic catastrophes. I think the silence is primarily the result of logistics. Interstellar travel and communication are extraordinarily hard. The return on investment is vanishingly small. And any civilization that has survived long enough to develop the capability has also survived long enough to ask the obvious question: why bother? A sufficiently advanced civilization would have extraordinary options available to it that don't require leaving home. A civilization that can manage the energy scales needed for interstellar travel can probably simulate entire universes in computation. They can explore mathematics. They can study their own solar system in extraordinary detail, and a solar system properly examined is a project that could occupy civilization for billions of years. They can develop art, philosophy, science, culture, relationships, experiences that make the cold emptiness of interstellar space look profoundly unappealing by comparison. Staying home isn't failure. Staying home might be wisdom. Now, here is where I want to pause because we've covered a lot of ground, and I want to make sure something hasn't gotten lost. Everything I've told you so far concerns what we currently know, and I want to be honest about the limits of that. Richard Feynman had a line he came back to again and again. I would rather have questions that can't be answered than answers that can't be questioned. He was deeply suspicious of certainty. He believed that the most important thing a scientist could do was maintain genuine, rigorous uncertainty, not fake humility that secretly harbored arrogance, but real openness to being wrong. So, let me be genuinely Feynman about this. Is it possible that the universe contains some phenomenon that would make interstellar travel as easy as driving to the grocery store? Yes, it's possible. Our understanding of physics, however extraordinarily well tested, might have gaps we can't yet see. But here's the crucial thing. The specific ways in which our physics might be wrong don't obviously point toward making interstellar travel easier. Every major revision in our understanding of physics over the past century, relativity, quantum mechanics, quantum field theory, the standard model has been confirmed by experiment at extraordinary precision. The speed of light as a limit has been tested to so many decimal places, in so many contexts, that overturning it would require not just a new theory, but a comprehensive demolition of the theoretical structure that underlies all of modern technology. Your GPS system wouldn't work without relativistic corrections. Your MRI machine wouldn't work without quantum mechanics. These aren't just abstract theories. They're the foundation of the material world we've built. I'm not saying it's impossible to be surprised. I'm saying the bet has to be calibrated. And the honest calibration, based on the weight of evidence, is interstellar travel at the speeds needed to make it practical is very likely not possible, and maybe categorically impossible. Which brings us back to Fermi's question. Where is everybody? Here's my answer. And I think it's probably right. Not in a comforting way, but in a clarifying way. They're home. Every civilization in this galaxy, every collection of creatures that ever looked up at the sky and wondered, every species that developed science and technology and the ability to ponder its own existence is almost certainly stuck in its own solar system, just like us. The distances are too vast, the energy requirements are too extreme, the timescales defeat any practical purpose, and the cost-benefit calculation, when honestly done, doesn't add up. We are not alone in the universe, almost certainly not. The universe is nearly 14 billion years old, 100 billion galaxies large, with more stars in it than there are grains of sand on every beach on Earth. The odds that we are the only self-aware things in all of that are vanishingly small. But we are effectively alone, not because we're special, not because we're isolated by some curse or some mystery. but because every civilization is effectively isolated. We are all islands in an ocean that is simply too wide to cross. I want to take a moment with this because I think it deserves one. There's a view of this situation that lands as pure bleakness. We're trapped. We'll never know who else is out there. We're dots of awareness separated by volumes of space so enormous that the word distance doesn't really capture it. We are each, in our own way, alone. I understand that reading. I've felt it. But there's another way to sit with it. If every civilization is isolated, then every civilization is entirely the author of its own story. There's no galactic empire to join, no advanced aliens to swoop in and fix our problems or destroy us on a whim. Whatever we build here, whatever we become, is ours. Entirely, irreducibly ours. And we have a lot to work with. Our own solar system, properly explored, is staggering. The Moon, Mars, the asteroid belt, containing enough metal to construct physical structures, orders of magnitude larger than anything on Earth. Jupiter and its moons Europa, with a liquid water ocean twice the volume of Earth's, possibly with chemistry going on in it right now. Titan, with its thick atmosphere and lakes of liquid methane. The deep outer solar system, full of objects we've barely looked at. We don't need other star systems. We have an entire solar system that we've only just begun to scratch the surface of. And beyond the physical, there's the universe itself available to our instruments, our mathematics, our minds. A universe that has been running its experiments for 14 billion years and whose results we're still reading. The deep sky surveys, the gravitational wave detectors, the particle accelerators, the radio telescopes, these are our ways of exploring a cosmos that we cannot physically travel, and they reveal wonders that science fiction never imagined. The silence of the sky isn't a wound, it's an inheritance. We are the universe looking at itself, from this particular vantage point, through these particular eyes. There are other eyes out there. We're quite sure other vantage points on the same incomprehensible whole. And they're looking back at their skies and thinking the same thoughts, asking the same questions, reaching the same conclusions. We'll never meet. And somehow, knowing that they're there, knowing that the process that made us made them too, that the same physics that built our atoms built theirs, that curiosity and wonder and the need to understand are probably universal features of minds that survive long enough to develop them somehow. That makes the loneliness feel different. Not smaller, but different. Feynman once said something to the effect that the universe is not only stranger than we imagine, but stranger than we can imagine. He was right. And one of the strangest things about it is this. The same universe that is vast enough to contain billions of galaxies and trillions of worlds is also constructed in such a way that almost none of those worlds will ever know about each other. The scale and the isolation coexist. The richness and the silence coexist. The universe doesn't care about our longing for contact. It just is what it is. And what it is turns out to be something like this. A place where life happens, where minds emerge, where the capacity for wonder flickers into existence in isolated pockets, separated by impossible distances, each one complete in itself, each one the only version of itself that will ever exist. I find that genuinely beautiful. In the way that true things are sometimes beautiful, not because they're comforting, but because they're true. So, the next time you look up at the night sky, maybe tonight, maybe on a clear night when you can actually see the stars instead of light pollution, here's what you're actually seeing. You're seeing other suns. Most of them have planets. Some of those planets probably have life on them. A small fraction of that life has probably looked up at its own night sky and wondered about the points of light it sees. And no one, not in the entire history of the universe, has ever actually met anyone from another solar system, or ever will. Not because the universe is empty, but because the universe is too full of distance. That's Fermi's paradox, and that's the universe's honest answer to it. Where is everybody? They're right where we are, looking up, wondering, alone together across an ocean of light years in a silence that may last until the last star goes dark. That's all for today on Feynman's Path. If this way of looking at things shifted something for you, if the sky looks a little different now, a little stranger, a little more real, then we did what we came here to do. I'll see you in the next one. Actually, wait. Before we go, there's one more thing I want to sit with. Because I think I've been too tidy about something. I've made the case that interstellar travel is practically impossible, that civilizations are trapped in their own solar systems, and that the silence of the universe makes sense once you do the math. And I stand by all of that. But Feynman would have my head if I tied this up too neatly, her gown pulling on the one thread that still bothers me. If the Great Silence is explained simply by the difficulty of travel, if every civilization just stays home and minds its own business, then we'd expect the universe to be fundamentally quiet. And mostly, it is. But in 1977, a radio telescope in Ohio picked up a signal, 72 seconds long, coming from the direction of the constellation Sagittarius, strong enough that the astronomer who noticed it in the printout circled it and wrote a single word in the margin: wow. The wow signal, as it became known, has never been explained. It has never been repeated. It fits the profile of what a deliberate interstellar broadcast might look like: the right frequency, the right bandwidth, arriving from deep space. It has also been the subject of several serious alternative explanations involving comets, terrestrial interference, and other mundane sources. The honest answer is, we don't know. I'm not telling you the wow signal was aliens. I genuinely don't think it was, and the lack of any repetition is a significant mark against it. But I'm telling you that the universe has, at least once, surprised us with a signal we couldn't immediately explain. And intellectual honesty requires acknowledging that. Here's the deeper issue. The search for extraterrestrial intelligence, SETI, has been running in various forms since 1960. In 60-plus years of scanning the sky, we found nothing definitive. That's often presented as devastating evidence against alien civilizations. But is it? Think about what we've actually searched. The electromagnetic spectrum is enormous. The sky is enormous. The number of possible frequencies on which a civilization might broadcast is essentially infinite. The directions we've surveyed in depth represent a tiny fraction of the total sky. And we've been listening for only 60 years, a cosmic eye blink. Absence of evidence in this case is not evidence of absence, it's evidence of the extraordinary difficulty of the search. There's an analogy I like here. Imagine you're standing in the middle of the Pacific Ocean, and you lower a coffee cup into the water. You haul it back up and examine the contents. No fish. Does that mean there are no fish in the Pacific Ocean? That's roughly the scale of our SETI search relative to the available search space. So what do we actually conclude? I think the honest position is this. The Fermi Paradox is not solved. It is, if anything, a living question, one that gets more interesting the more carefully you examine it. The physics of interstellar travel makes casual contact essentially impossible. The math of the galaxy makes it nearly certain that other life exists. The silence of our radio telescopes could mean 1,000 different things, and we don't have the evidence yet to choose definitively between them. What Feynman would have hated, what I want us to resist, is premature closure on either side. The people who say the universe is certainly teeming with civilizations and they're just hidden for some reason are telling a story. The people who say Earth is cosmically unique and we're genuinely alone are also telling a story. The honest position sits in the uncomfortable middle. We have good physical reasons to think contact is impossibly hard, good statistical reasons to think we're not alone, and exactly zero confirmed evidence of anyone else. That's the real answer to where is everybody. We don't know. And that not knowing properly felt, properly inhabited, is not a failure, it's an invitation. The universe handed us a mystery so large that every generation of humans since Feynman scribbled on that cafeteria napkin has been unable to resolve it. We've built better telescopes, faster computers, deeper theories. We've listened harder. We've looked wider. We've thought more carefully. And the question remains. There's something almost consoling about that. A universe that keeps its secrets is a universe that keeps giving us reasons to look. Every time we refine our instruments, every time we improve our theories, every time we send out a new probe or build a new observatory, we're participating in the longest-running question in the history of our species. Are we alone? We don't know. We keep asking. We keep looking. That's what Feynman's path looks like in the end. Not certainty, not comfortable answers. A burning question, a rigorous method, and the courage to sit with the silence long enough to actually hear what it's telling you. The stars are out there. The silence is real. And somewhere, maybe just maybe, something is looking back. Now I'll see you in the next one. But I realize I've been dancing around something that deserves a direct confrontation. I've been talking about the physics of interstellar travel as if that's the primary reason we don't see aliens. And it is important. But there's another piece of the puzzle that I've only grazed, and it's the one that keeps physicists and astronomers awake at night more than almost anything else. It's called the Drake equation. Now don't worry, there's no math here. The Drake equation is less an equation and more a way of organizing our ignorance. Frank Drake invented it in 1961 for the first serious scientific conference on the search for extraterrestrial intelligence. He wanted a framework, a way of asking, given everything we know about stars and planets and biology and civilization, how many communicating civilizations might exist in our galaxy right now? The equation breaks the question into pieces. How many stars form per year? What fraction of them have planets? What fraction of those planets could support life? Of those, on how many does life actually appear? Of those, on how many does intelligent life develop? Of those, how many develop technology? And how long do those civilizations typically last? Drake was being clever. He wasn't trying to get a definitive answer. He was trying to map out where our ignorance lived, which parts of the question we could answer, and which parts we couldn't. In 1961, almost every term in that equation was a mystery. We didn't know how common planetary systems were. We didn't know how life originated. We didn't know if intelligence was an inevitable outcome of evolution or a cosmic fluke. Over the last 60 years, the first few terms have resolved dramatically. We now know that planets are extraordinarily common. Almost every star has them. We know that many of those planets sit in the habitable zone, not too hot, not too cold for liquid water. We know that in our own solar system, the ingredients for life are abundant. Complex organic molecules on comets, on asteroids, on Titan, on Mars, potentially in the plumes of Enceladus. Life on Earth appeared remarkably quickly after conditions permitted it within a few 100 million years of the planet's surface solidifying. Which suggests that, given the right conditions, life might not be particularly hard to start. All of which implies that life in the universe is probably not rare. Not everywhere, but not rare. And here is where the equation takes a turn. Because the final term, the one Drake himself identified as the most uncertain, the most consequential, and the most disturbing, is the lifespan of a technological civilization. Call it L. How long does a civilization that has developed radio technology and industrial capacity and the ability to destroy itself, how long does it actually survive? If L is large, if civilizations typically last millions of years once they develop technology, then there should be millions of them in our galaxy right now, and the silence becomes very hard to explain. If L is small, if civilizations typically last only a few hundred or a few thousand years before destroying themselves, or burning out, or simply going quiet, then the silence makes more sense. There might have been many civilizations before us. There might be many more after us. But at any given moment, the number simultaneously broadcasting might be tiny. And here is the thing that nobody at that first 1961 conference could avoid noticing. The Drake equation was published in the same era that humanity first developed the ability to annihilate itself. Nuclear weapons. The capacity for civilization-ending war. The question of how long technological civilizations survive became, suddenly, extremely personal. Feynman lived through the Manhattan Project. He helped build the bomb. He was at Los Alamos. And in the years after the war, he talked about something he noticed in himself, a strange detachment from the future. He'd be walking through a city looking at new construction, and he'd catch himself thinking, why are they building that? Don't they know? Don't they know how close everything is to being gone? That feeling has never entirely left our species. We are the first civilization in Earth's history to have developed the ability to end it, and we have been in possession of that ability for less than 100 years. The Fermi Paradox, viewed through this lens, takes on a different texture. Maybe the silence isn't primarily about travel times. Maybe it's about survival. Maybe the universe is full of civilizations that reach a certain critical threshold, the point where their technology can either destroy them or launch them into a long future, and most of them don't make it through. This possibility is called the Great Filter. The idea that somewhere in the chain from simple chemistry to starfaring civilization, there is a filter, a bottleneck, an obstacle that almost nothing makes it through. If the Great Filter is behind us, if the hard step was, say, the emergence of complex multicellular life, or the leap to eukaryotic cells, or the evolution of a nervous system, then we are extraordinarily lucky. We made it through the filter. The future might be genuinely open. But if the Great Filter is ahead of us, if it's something that technological civilizations tend to encounter and fail to navigate, then the silence of the sky is not reassuring at all. It's a warning. Physicist Stephen Webb wrote a book, cataloging 50 different solutions to the Fermi Paradox. They range from the optimistic to the terrifying. Aliens are hiding. aliens are signaling in ways we can't detect. Aliens have transcended physical space. Aliens destroyed themselves. There is no intelligent life besides us. We're living in a simulation. The physics of consciousness means intelligence is far rarer than biology. Civilizations go inward rather than outward, preferring virtual experience to physical expansion. Each of these explanations has serious proponents. None of them is obviously ruled out. And here is what I find genuinely moving about all of this, when I let myself feel it fully rather than just think it. We are a young species asking the oldest question. We have been on this planet for perhaps 300,000 years. We have had anything like science for maybe 500 years. We have been capable of interstellar communication for less than a century. We are, in cosmic terms, newborns. And we are smart enough to have formulated a question we might never be able to answer. That's a remarkable thing. It requires no religion, no mysticism, no appeal to anything beyond the physical universe to find that remarkable. It is remarkable on pure physical grounds that the atoms of a collapsing star, over billions of years, arrange themselves into something that can wonder about collapsing stars. Feynman was asked once, in an interview, about the experience of not knowing something, about living with an open question. And he said, I'm paraphrasing here, not inventing that he found the not knowing more interesting than any possible answer, because any specific answer closes a door. Not knowing keeps infinitely many doors open. The Fermi Paradox keeps every door open. Maybe we're alone and the universe has produced exactly one experiment in self-awareness, here, on this small wet rock, and everything depends on what we do with it. Maybe we're one of billions of isolated islands of consciousness, each developing its own understanding, its own art, its own questions, all of us looking out at the same stars from different angles, all of us alone together. Maybe the universe is running a kind of experiment in which isolated civilizations each develop answers to the same deep questions independently, and the answers themselves are what matter, not the communication of them. I don't know which of these is true. Nobody does. What I know is that tonight, when the sky is dark, you can walk outside and look up and see light that has been traveling for years, for centuries, for thousands of years, to arrive at your eyes in this particular moment. Some of that light comes from places where, right now, something might be wondering about the same questions you're wondering about. Something made of the same atoms, operating under the same physics, looking at the same darkness, you'll never meet. You might never even know of each other's existence. But you're both there, both looking, both asking. That's not nothing. That's actually something quite extraordinary. This has been Feynman's path. I'll see you in the next one.